All right, so the first thing we have to talk about when we start looking at motion, right? Today we're going to start looking at how things move, right? How things move. That's what most of chapters 1, 2, and 3 really deal with, is how things move. How fast, how far, how long, right? Those are the types of questions we answer for chapters 1 through 3. And then we'll lead into chapter 4, which deals with forces, which starts to ask the question as to why are things moving, right? What forces put this object in motion, all that kind of stuff. So we've got to get a bigger picture of what motion is, right? Motion is everywhere. It's scientifically proven that your eyes are just attracted to things that are moving, right? Naturally, without even thinking about it, your eyes follow things that are moving. And so motion's an everyday part of our life, right? We are attracted to what is in motion, and we're interested in what's in motion, okay? So we have to start thinking about what is happening to that object that's in motion, okay? When an object in motion, its position is changing, right? Its location is changing. And so we've got to start using that term position in terms of its location, right? Where is it? How far has it gone? All that kind of stuff. So we'll hear that word a lot, but its position is changing. There's going to be a couple different ways that position can change. A straight line motion is where we're going to start. That's just simply from point A to point B, right? It can go fast, it can go slow, whatever it does. We can have circular motion. We can have arc type motion. Okay, arc type motion would be things that go up and come back down. That's otherwise called a projectile, right? Have you heard that term before? Projectile motion is things that travel both horizontally and vertically. And then you've got something called back and forth motion, or called simple harmonic motion. A back and forth motion would be like a pendulum. It could be anything. Do you know what a pendulum is? Right, like at the end of a clock, right? That swings back and forth. Back and forth motion could be that type of motion, or it could be anything that vibrates. All of that is considered simple harmonic motion. And so we're going to kind of walk through analyzing these 4 types of motions kind of throughout the whole year. So we'll start with straight line motion, things that move very simply in a straight line from point A to point B. We'll actually go into arc motion next. Then we'll look at circular motion, and then we'll kind of finish with simple harmonic motion. So we'll see all types of how things move. Okay? Straight line motion is the simplest path. It always relates to a place and a time. So where is that object at, and how long did it take to get there? Right? It's always going to be related to a place and a time. And so point A to point B here with this like image can be very, very simplistic, right? They move from point A to point B, but it could be a reality that that car did several things in between there to get from point A to point B, right? It could have stopped in the middle. It could have went backwards. It could have gone past point B and then ended up back there at point B. So there's a lot of things that could have happened behind the scenes of this simple diagram, but realistically in physics, what we care about is not the path it took to get there. We kind of care about the beginning and the end, right? And that's pretty much it. It doesn't really make a difference to us how the object got from point A to point B, right? In some situations it does, but most of the time it doesn't. So the reason I put this up here as well is that we're going to start diagramming motion. Okay, you don't even have to draw the car, just a little line telling us from point A to point B. We're going to start diagramming motion, and at first those diagrams will start very simple like this, and then they'll start to get a little bit more complex, but we will start diagramming that so it can give us a visual of what's happening in that motion. Okay, we're going to do our motion diagrams most of the time in a graph. Okay, using a coordinate system. So hopefully you guys feel pretty comfortable when I say coordinate system, right? Which directions are the positives on this coordinate system? To the right, and then what else? What other direction is the positive direction? Up. And so then this is negative and negative directions. We're going to use that coordinate system for pretty much all of our motion. We also need to feel pretty comfortable eventually with labeling them with cardinal directions. So this would be north, east, south, and west. Do you feel pretty comfortable with the cardinal directions? I'm talking about in like 2 dimensions on paper. I don't need to know if you're good at them like driving around, okay? But on paper, we got to know which directions, north, east, south, and west. So north and east will always be our positive coordinates, and then south and west are both our negative coordinates, okay? So when we start diagramming our motion, we deal with the coordinate system, and you get to pick an origin, okay? You get to pick the origin. So this is really an important concept for our motion, okay? I want you to kind of visualize an object that we'll start to see this in when we start dealing with projectiles. So let's say somebody's on the top of a cliff or a hill or whatever, and they throw an object off the side of the cliff. Right? It lands down there. Those are the types of problems we're going to be doing. This is as complex as your diagram needs to be. But what we have to start thinking about is, well, where is my origin, okay? And so what I'm really going to insist with our origin is that our origin is at the beginning of the motion. I don't always choose the ground to be the origin. I don't always choose the lowest point to be the origin because I want to be able to identify, well, what did my object do? Did it end up far away from where it started? Did it end up below where it started? Did it end up above where it started? Whatever it might be. So I like to pick the origin to be where our motion begins from. Okay, and I'll say that kind of over and over again, but it's kind of a personal preference, but I always do it the same way. Okay, so that I'm consistent, but I'll always choose my origin to be where my motion begins from. So that means if in another case, I'm standing on the ground and I throw an object into the air, right, this would be where my origin is. Okay, so it always kind of depends on where your motion starts from. Huh?
So if you get to pick the origin, how is there a concrete answer? Because if your origin's different than mine.
Right, okay, good question. So let's say that, let's go back to the one on the cliff. Okay, so if I want to know how tall the cliff is, right? My origin is here. My y variable is going to come out to, let's say, negative 30 meters. So that tells me that this cliff is 30 meters tall, right? So I just flip my answer to answer the question. If someone would have chose their origin to be here, they would have found out that their final height was 0, but they could calculate, well, how tall was my highest point, or how tall did I start from? So there's lots of different ways that you can answer the question or get to your final answer. There's not just you have to use this equation in this order. It doesn't work that way. So that's a good question. But we'll always be able to kind of flip our answer around in terms of using the positive or negative because it's just about direction. Yeah, good question. Okay, in straight line motion, we've got two different terms here that we're going to have to learn and differentiate between. Distance is the total amount of length that we cover. Okay, the absolute total amount of length that we cover. And then displacement, that's a new term for us, I think. Displacement is new. Okay, displacement means something different. Displacement is how far we are from where we started.
Like the origin?
Yeah, from the origin, right? How far we are from where we started. And so this is where distance and displacement can get a little bit tricky because they seem at face value to kind of mean the same thing. Right? Total distance traveled or total length traveled versus how far we are from where we started. Can you think of an example in which those two things would be different? Yeah.
Well, I think example you gave was the car moving from point A to point B.
Mm-hmm.
If it went past point B and then came back.
Yeah. Right. So if my car really traveled here and then back, we would have different distance and displacement. Right? Think about you starting at the starting line and running around the track one time. Right? You ran a distance of 400 meters, but realistically your displacement is 0 because you ended up exactly where you started. Okay, so they mean two very different things. Most of the time, not most of the time, 98% of the time, we deal with displacement. Okay, we don't really deal with distance, we deal with displacement. Because like we talked about, it's not really a concern to us as to how we got from point A to point B. We're really just concerned about the start and the finish. Okay, so for the most part, we'll be looking at displacement. Okay, so displacement is how far you ended up from where you started. The variable, I wrote this wrong, this is not equation. The variable for displacement is an x. Okay, why do you think we label it with an x versus a y? Why do you think they label it with an x versus a y? Yeah, because we're starting with horizontal motion. So along this x-axis, if I'm talking about a coordinate system and my person has moved 5 meters, right? We've moved 5 meters in the x direction. So we label displacement with an x. When we start dealing with vertical motion, we will label it with a y. Okay, and so we'll have situations in which we've got both of those variables. We've got an x and a y if my object moves both horizontally and vertically. So we'll get to that point later in chapter 1 when we've got both sets of those things. Does that kind of make sense? So horizontal displacement is an x and vertical displacement is a y. Okay. All right. This displacement is what we consider a vector quantity. A vector quantity. Okay, and so vector quantities are any measurement that requires both magnitude and direction. Okay, so that displacement is just an example of a vector quantity. Okay, vector quantities mean they are any measurement that has to have both magnitude and direction. So do you know what we mean when we say magnitude? It just means like the size or the number, okay? So if I say the displacement is 10 meters south, this would be my magnitude, and this would be my direction. Okay, so you have to have both of those things when we deal with displacement. Okay? We can also indicate direction with a positive and a negative. So we get, in physics, we get to use positives and negatives only purely to indicate direction. There's no such thing as a negative value of length. You know what I'm saying? Like you can't have negative length. Agreed? Right? Something can't be smaller than 0. So the negatives that we have just tell us direction. So if I said that my object was negative 10 meters from where it started, we would have to know, well, is that south of where it started or is that west of where it started? But it gives us a clue as to the direction. Okay, it does not have anything to do with the number itself. So the direction that we're given can be either cardinal directions or it could be positive, negative, depending on the situation. Okay, when we draw a vector, any kind of vector that we draw is always represented by an arrow. Okay, it's always represented with an arrow, and that arrow should technically be drawn to scale. So we're going to practice drawing to an exact scale, and we're also going to practice drawing to just a proportional scale. Okay, do you know what I mean when I say proportional scale? Like if I say I went 10 meters east and then 5 meters south, are those drawn to scale? No, because my 5 meter vector should be half as long as my 10 meter vector. Does that kind of make sense? That's what we mean when we say drawn to scale. That's going to be the proportional type of scale that we use most of the time. It'll be very rare instance where I ask you to draw to an exact scale. And if it was the case for that, I would give you a ruler to do that. And we'll practice that here in just a little bit. But you would need a ruler and you would need to have like a key and everything to draw to actual scale. We'll practice that. It's just not something we have to use all that much. Okay. Practically, it's much easier to just draw to a proportional scale because it gives you a better idea or a quicker idea. Okay. So vectors are any type of measurement that has to have magnitude and direction. Displacement is the first type of those measurements that we've covered. Velocity will also be a vector. Acceleration will also be a vector. So we're going to cover lots of different things that are considered vector quantities. Okay, so the pair that goes with that, the opposite kind of vectors, is something called a scalar. A scalar measurement or a scalar quantity is something that only requires a magnitude. It does not require direction. Okay? So, for example, distance is one of those quantities. We talked about how distance is the total amount of length covered. And if we go back and forth, we jog back and forth several different places, we can't give a single direction with that. Right? So we can't give a direction with distance. It's just the magnitude itself. So we can say we ran. Think about running around the track, right? We ran 400 meters, but we ran in a lot of different directions while we were covering that oval. right? We started out going one way, and then we had to curve, and then we were going the completely opposite way, and then we had to curve again, right? So that includes a lot of directions. So scalar quantities don't have that, okay? Time doesn't have a direction. Temperature doesn't have a direction. Any negative that goes with temperature has to deal with a numerical value, not the direction of it, okay? All right, any questions about the difference between vectors and scalars? We very rarely deal with scalars. We would much rather deal with vectors because it has the direction included, okay? So let's talk a little bit more about vectors here. Vectors can be what's called added graphically. I don't know if you guys talked about this in pre-calc at all. Did you do vector addition in pre-calc? No, okay. It might be something that you see later. I don't really know if you do that or not. But vectors can be added graphically. And so I'm going to walk you through kind of the steps to add vectors, and then we're going to practice with that. So we need to draw vectors to scale, okay, to a proportional scale as best we can. Okay, vectors are added using a certain method. There's a certain pattern that has to be followed, and it's called the tail to tip method. The tail to tip method. And so what that means is that the tail of the second vector adds on to the tip of the previous vector. And I'll show you what that looks like, but it's really important, and I'll kind of get as to why. But the tail is always the starting point of the motion, and the tip is always in the direction of the motion. So that sounds a lot more complicated than it is. Here's my origin. If I'm moving to the east, my vector just needs to look like this. Starts at the east and moves to the east. Or starts at the origin and moves to the east. Okay, so it sounds more complex than it actually is, but this end right here would be considered the tip of the vector. This end would be considered the tail of the vector. Okay, so let's look at adding them graphically using what's called the tail to tip method. Let's say I've got several different vectors here. 10 meters east, 3 meters south, 4 meters west. Let's say I want to find out, if I follow this path, how far am I going to be from where I started? Okay? So if I draw my origin here, I'm going to draw 10 meters east. Let's say I now go, I need 3 meters south, so I need to draw them 3 meters south and then 4 meters west. That's roughly 4. Okay, so my final ending point is here. So in this situation, will my distance and my displacement be the same? No, because my displacement realistically is only from here to here, right? It only looks like I went this far. So my distance is 17 meters, but my displacement is however long that vector is. Does that kind of make sense? Okay, so here's why we add them tail to tip like that. That right there is tail to tip method. First one, second one's connected, third one's connected. If I didn't draw them like that, it would look like this. 10, 3, 4, right? Does that lead me anywhere? No, right? I'm not going anywhere from the origin. So the reason we add them tail to tip is so that we can figure out where are we actually ending up from the origin, right? If I just do this, I can figure out where I'm ending up, but it's not a clear picture. So we have to add them tail to tip. Okay, sometimes we remember it now, and then like we get later in the year and we've like forgotten this part of it, but it's really important. Okay, so we add them one right after the other. What about this question? Does it matter the order in which I add my vectors? Do you think it makes a difference the order in which I add them? Okay, so if we think, let's go 4 west, 3 south, 10. Does this vector look the same as this one? Yeah, they look the same, right? So it makes no difference what order we add our vectors in whatsoever. So that's an interesting part of it, is that it doesn't matter the order in which we add them. They can go in whatever order you want because the end result, that final displacement, is the same regardless of what order you put them in. Okay? I think I talk about that later, so I might have been ahead of myself, but here. Okay, So this last vector that I drew, that colored vector at a diagonal, that's considered what's called the resultant vector. It is the graphical sum of all of our vectors put together. Okay, the resultant vector. That's an important vocabulary term here for us. It's considered the graphical sum of all of these vectors in a diagram. It always goes from the origin to the tip of the last vector. Okay, it always goes from the origin to the tip of the last vector. So let me pull that example up again. I've got a resultant vector in both diagrams. In this diagram, which color vector is my resultant vector? The purple, right? It tells me where am I ending up versus where I started. It goes from the origin to the tip of the last vector. And then in this diagram, what's the color of my resultant vector? Red. Okay, very good. So we draw all of them out. Then we draw one final vector from the origin to the tip of our last one, and that gives us a resultant vector. So the same situation is true here. If I were to draw them not tail to tip, 10, 3, 4, where does my resultant vector go? Right? I don't have anywhere for my resultant vector to go. I don't have a tip of the last vector because they're all pointing different directions. So that's a problem. Okay, let's try an example here. I think I printed that for you. Okay, good. All right, so let's say we start at the origin. We run forward 2 meters. So which direction would we consider forward here probably? East. Yeah, east is going to be forward. So 2 meters forward. You draw that vector. Then they go backwards 6 meters. So do I start again at the origin? No, I'm just going to start right here and go back 6. 1, 2, 3, 4, 5, 6. Then I'm going to pick a different color. Forward 4 meters. 1, 2, 3, 4. I'm back to where I started. Then we go forward 5 meters. So 1, 2, 3, 4, 5. That's where I end up. Okay, so what is my let's go ahead and draw a resultant vector here. What would the resultant vector look like? It would actually look exactly the same as my final blue vector, right? That's coincidental. That doesn't happen all the time. But I started here and I'm ending up there, so there's technically my resultant vector as well. Okay? So what is my displacement here? What's my final displacement? How far am I ending up from where I started?
5 meters.
Right, plus 5 meters, or you could say 5 meters forward or whatever, but we got to include that direction there. I will say if you leave the plus off, it's assumed, right? If you just leave the number as positive, it's assumed that it's forward, so you don't have to put that positive on there. If it's going backwards, we definitely need to include the negative or the cardinal direction that goes with it, okay? So my displacement is 5 meters, but what's my distance? What'd you say? 17 meters, 8 plus 9, 17 meters, okay? My total distance is just given with D. My total distance would be 17 meters, and we don't include a direction with that, okay? Because we went lots of different directions. So in this case, I went 11 kilometers north, then 11 kilometers east. 11 kilometers north, then 11 kilometers east. So let's call each of these segments 2 kilometers. So I start here at the origin. I'm going to go 2, 4, 6, 8, 10, 11. 6, 8. Yep, okay. And then I'm going to go east. So do I start back down here and go east? No. Okay. I have to go up here and then go east 11. So my resultant vector has to go where? From the origin to the tip of my last vector. I can't draw a straight line. There we go. Okay, my resultant vector, again, is my purple one here. So I want to actually calculate now my resultant vector. How do I know how long that is? Is there a way I can solve that? Right. What's that called? Pythagorean Theorem, right? A squared plus b squared equals c squared. Okay, you're going to have to be really good at Pythagorean Theorem. Okay, we're going to be really good at solving right triangles. Like really good. Okay, so let's go ahead and do that. Go ahead and solve that. It would be 11 squared plus 11 squared equals c squared. So grab your calculator out if you don't have that out, and let's go ahead and calculate what that side's going to be. Could it be smaller than 11? No. Right, good. Our hypotenuse can't be smaller than either of our sides. I got about 15.6. Okay, realistically, I should round that to a whole number or two significant figures. So let's call it 16 kilometers because of significant figures. Okay, that gives me 16 kilometers is my displacement. But what direction am I going? Right? Northeast. I am going northeast, but unfortunately northeast is not specific enough. So we have to do one more step. We have to find what's the angle in which we left the origin. Okay, we have to find the angle in which we left the origin. So now we've got to use a trig function, sine, cosine, or tangent, to help us solve that angle. Okay, I'm going to recommend that we use tangent because these sides were given to us. If we would use hypotenuse that we solved for and we were wrong, then we're wrong twice now, right? So I'm going to recommend that when we solve for this angle, we use tangent. So let's just review. Do we need to review trig functions, or do we feel okay about that? Sine is opposite and hypotenuse. Cosine is adjacent and hypotenuse. Tangent is opposite over adjacent. So if I was going to solve for this angle, I would say tangent of my angle, theta, equals opposite over hypotenuse. So since I'm solving for theta in my calculator, what do I have to do differently? Yeah, very good. So I'm going to go second tangent, -1 of 11 over 11. Okay, that's what it's going to look like. We're going to use this a lot. Second tangent of 1, really. Oh, we didn't even have to calculate that. That was silly. But whatever, we did. Yeah, we should have known. I should have known. Obviously, it was a 45-degree angle, but I wasn't thinking. Okay. How do we know that it's a 45-degree angle? Yeah, the sides are the same. That was I wasn't thinking. But if we don't know that it's a 45-degree angle, we're going to plug in opposite over adjacent. So, okay, always degrees in this class. So if you're in calc, you might be in radians in there, and then here you're going to have to switch it to degrees. Do you know how to switch them? Okay, this class always needs to be degrees. So I'll remind you of that as on tests, like when we need to use it, because it stinks to do the whole test in degrees. Or in radians, I mean. Okay, so here's how we report our final answer here. Okay, our final displacement would be 16 kilometers at 45 degrees. And then we've got to give the cardinal directions for that angle. So here's how you give the cardinal directions. We look at this angle right here, right? This is the one we're looking at. Is that angle north of east, or is that angle east of north? This one in particular, right here, is east of north. Okay? So our final answer would be reported like this, east of north. Okay, here's how that works. Here's our cardinal directions, north, east, south, west, okay? I'm going to see what axes is my angle touching. What axes is my angle touching, north, east, south, or west? It's touching the north axes, agreed? Right? This angle right here is touching the north axes. So then I decide, okay, does my triangle swing east of north or west of north? Right? My triangle swings east of north. So that's how I go about determining it. You could also say, well, I went north first, then east, so then I write it backwards. Right? I went north first, then I went east, so my angle is east of north. You can do it that way too.
So why do we round for
About finding the angle and the direction on that one. We're going to get into much more complex problems with that later, but I wanted to introduce it here. Okay? So this would be our final answer on how we would report that. We ended up 16 kilometers away at 45 degrees east north. So that tells me if someone wanted to start at the origin and end up exactly where I did, they didn't have to go all 22 meters. They could leave 45 degrees and end up at the same point. Okay? All right. Okay, velocity is when we find a rate. It is a rate. Okay, so velocity is any change in displacement divided by change in time. So here's our first equation. Okay, this is for, so if you want to organize them by chapter, you can. This is chapter 2, technically. If you want to order them by topics, this topic you might call it kinematics. We're going to get 3 bigger kinematics equations later, but you could label it with kinematics if you want. You could just call it motion. I don't care what you call it, but this will be the first one that goes on there. So velocity equals change in displacement over change in time. Do you know what this little symbol, this Greek letter is called? Yeah, it's called delta, but it means change in. And it always means what minus what? Final minus initial. We'll always do final minus initial. So realistically, since we always choose the origin to be at the beginning of our motion, our initial displacement is always 0. Right? So most of the time, you're really not going to have an initial displacement. It's just going to be whatever your final displacement is over time. The same thing is true with time. We don't talk about how the motion started at 10 seconds and it finished at 50 seconds. That's not how questions work, right? We say it took 40 seconds for it to happen. So it's very unlikely that you would ever have an initial time. You could have an initial displacement, but not always. Okay, so most of the time it's just going to be displacement over time. This means it's called delta, but it means change in. So it's final minus initial. Final minus initial. This equation also is only true for objects that are moving at constant velocity. If we had objects that were speeding up or slowing down, we would not be able to use this equation. We'd have to use a different one that we'll get to later. Okay, so this is for constant velocity. You might want to you can put that down as well, but this is for constant velocity. So it'd be like if you had the cruise control set, right? You could use this type of equation. Okay, it's a vector quantity, which means it has to have what 2 things? Direction and what else? Magnitude. Good. It's got to have magnitude and direction. Okay? So if it has to have magnitude and direction, what would it mean to have a negative velocity? Would it mean we're slowing down? Would it mean we're speeding up? Would it mean we're going forward, going backward? What's it mean? Yeah, going. All it means is that we're moving in the negative direction. So it means either south or west. It does not mean that it is slowing down. Okay, negative does not mean slowing down. For some reason, that's kind of a preconceived myth. But negative velocities does not mean that it's slowing down. It just means that it's going backwards or it's falling through the air or whatever it might be. Okay, so it's moving backwards. The unit for velocity is meters per second. Okay, or any other sort of length per time thing. It could be kilometers per hour, right? We did that conversion to go kilometers per hour to meters per second. We most of the time want them in our equations to be meters per second. But either way, if this is meters per second, that means x would need to be meters, time would need to be seconds, right? Those units just have to match within that triangle type equation. Okay, let's go ahead and try one here. A car travels with a velocity of 50 meters per second for 2 minutes. They then turn south and travel 30 meters per second for 2 minutes. What was the total amount of distance covered? What was the total distance covered? So we've got 2 different situations here. We've got a situation where they traveled 50 meters per second and then 30 meters per second. We've got to solve them in separate equations. We can't solve them in one. Okay? So I'm going to go ahead and set up our equation here. For the first segment, my velocity is 50. My displacement or my x value is what I'm solving for. And then how much time did it take? Right, it took 2 minutes, but realistically, I need that in seconds. So that comes out to be 120 seconds. Right? So in the first segment of my motion, 50 meters per second equals x over 120. How do I go about solving for x there? Do I divide or do I multiply? Multiply by 120, that cancels it on this side. Multiply by 120 over here, which means my x value is 6,000 meters. And I know it was going east because that's what it told me I was traveling. 6,000 meters east. Okay? Any questions about how we set that up? The second segment says I traveled 30 meters per second for 2 minutes. So my velocity equals 30. My x value is what I'm solving for, and my time value is, again, 120 seconds. Okay, I like to build my little list over here, right? It gives me a clear picture of what I'm looking for and what I already have. So I encourage you to put in, especially the one that has the question mark, right? What am I looking for? So my velocity is 30 equals x over 120. Again, I'm going to take that 120 and multiply it out on both sides. And so that gives me an x value of 3,600 meters. And then what's my cardinal direction here? South, right? It tells me I turned south. So now I've got a question to answer in terms of distance. What do I have to do to just find the distance? All I have to do to find distance is just add them up because I'm not concerned about direction here. So 6,000 plus 3,600 is 9,600 meters. And do we put a direction with distance? No, right? We don't put a direction with distance. So that's the answer for the first part of our question. However, it goes on to ask me, what is the displacement? So now I've got another step that I've got to do. I've got to draw out my motion here. I went 6,000 meters east, and then I did 3,600 meters south. And so now to find my displacement, I've got to draw my, what's this purple vector called?
Resultant.
Good, I got to draw my resultant vector. And I have to find out what's the value of my resultant vector, and I've got to find the angle that goes with that. Okay, so how do I go about solving for that side of my triangle? Right. Can you guys plug that into your calculator in one step? 6,997. All my other values are to the whole number. So I'm going to round that to the whole number. Again, I'm not going to be super picky about significant figures. It'll be something that I kind of forget about because I like it to be a little bit more exact. But in reality, they were given to the whole number. But we're going to say it traveled that many meters, and then we've also got to give the direction because we're talking about displacement. And southeast is not specific enough, so we need to find the angle that goes with that. We're looking for this angle right here. So I'll go second tangent of opposite, 3,600 over adjacent, which is 6,000. And that gives me an angle of 31 degrees. What of what? South of east. Very good. South of east. I determined what axis is my angle touching. It's touching the east axis, and then I decide did it swing north of east or south of east, and that triangle clearly swings south of east.